Hello everybody, I welcome you to my second lecture on network functions. In today's lecture, we shall solve some tutorials on network functions. So, the first example, let us see, has asked us to find the transform impedance of this given network. So here we have resistor of 5 ohms, inductor of 2 Henry and capacitor of 1 farads. First, in order to find transfer impedance, we have to represent this in Laplace domain. So resistor value will remain same. Inductor, as you know, is represented by Ls and capacitor is represented by 1 by Cs in impedance. So L value is 2, so its value becomes 2S. Capacitor C value is 1, so in Laplace domain its value becomes 1 by S. So since all are in series, I can write Z of S is nothing but 5 plus 2S plus 1 by S. So if I take LCM, Z of S would be nothing but 2S squared plus 5S plus 1 by S. So this is the transform impedance of this network. So in this case, we should remember that initial conditions are all assumed to be 0 while doing network functions. The second example has asked us to find transform admittance of a parallel network RLC. So here, if I convert this into Laplace domain, 10 ohms remains the same. 1 Henry becomes 1 into S and 2 farads becomes 1 by 2S. So that is in impedance. But if I want in admittance, then 10 becomes 1 by 10, inductor becomes 1 by SL and capacitor becomes CS. So therefore here we represent in admittance. So 1 by 10, here this becomes 1 by Ls, L value is 1, here CS, C value is 2. So since I want admittances, we know that if admittances are in parallel, we can add them, which will give me the total admittance of this entire network. So if I want total admittance, I'll add Y1 plus Y2 plus Y3. So on adding all the three values, I'll get transform admittance. Y of S is equal to, if I take LCM, it is 2S squared plus 0.1S plus 1 by S. So if I want transform impedance for the same sum, it is nothing but reciprocal of this Y of S, that is nothing but S by 2S squared plus 0.21S plus 1. This is the one way of doing the sum. So the other way we can do is, first if you want, you can find the value of Z of S and then reciprocal that value. That is up to you. So if I want to first find Z of S, I can calculate the parallel combination of all these elements, which will give me Z of S value, and reciprocal of that value will give me Y of S. So in either the way we can solve the sum. The third example is asked us to find a driving point impedance for this one port network. So driving point impedance, that is Z of S is equal to V of S by I of S, we should find. First let us convert this into Laplace domain. So this value becomes 2, inductor value becomes 5S, capacitor value becomes 1 by S and resistor value remains same. So these two are in parallel, so this parallel combination will give me 4 by 1 plus 4S, and this parallel combination is in series with these two are in series, so this I can write as 2 plus 5S. So these two are in series, so this Z of S I can write as 2 plus 5S plus 4 by 1 plus 4s. If I take LCM, which will give me the value of z of s to be 5s square plus 3.2s plus 1.5 divided by s plus 0.25. So here, after taking LCM, you can take 4 common, which will give me this expression. So the next example, so we have an RL circuit and in parallel with the capacitor 1 by Cs. So here directly he has given in Laplace domain. So he has asked us to find input impedance, which is nothing but equal to driving point impedance. So here these two are in series, that is R plus Ls, which is in parallel with 1 by Cs. So Z1 Z2 by Z1 plus Z2. If I represent Z of s in that manner, so we will get R plus Ls by 1 plus RCS plus LCS square. So here in the numerator I have to take L common. In denominator, if I take LC common, then it will give me this expression for input impedance. The fifth example, the driving point admittance. So here I want admittance. So first let us transform this into Laplace transform. So 1 by 2 farads becomes 2 by s. 1 Henry is nothing but Ls, so it is values is s. 1 by 4 farads is 4 by s, and inductor 2 Henry will become 2s. So since I want admittance here, let us consider admittance values of these parallel branches first. So y1, so if z1 is equal to 4 by s plus 2s, obviously y1 will be reciprocal of that value. So 1 by 2s plus 4 by s. Since z2 value is s, so if I want y2, it is a reciprocal of 1 by s. So on adding these two values, which will give me the admittance of this parallel combination, which is nothing but 3s square plus 4 by 2s square plus 4s. So if I want impedance of this parallel combination, I can write 1 by ys, which is this expression. So either we can do in this manner, or directly if I want impedance of this parallel function, I can represent as z1 z2 by z1 plus z2. So now that is in series with your 2 by s. So that value I have added with 2 by s, which will give me the transform impedance of this function. So transform admittance is nothing but reciprocal of this function, which will give me this expression. So this is the transform impedance and admittance of this function. Next, sixth example, I have to find transform impedance. So first let us transform this in Laplace domain. So 10 ohms and 20 ohms will remain same. 2 Henry will become 2s, and 5 farads will becomes 1 by 5s. So these two are in series, 20 plus 1 by 5s, which will be in parallel with 2s. So therefore 2s into 20 plus 1 by 5s divided by 2s plus 20 plus 1 by 5s. And this combination is in series with 10 ohms, so which will be added to 10 ohms. So on simplification shall give me the transform impedance of this network. So next, the seventh example. So here we should find the driving point impedance as well as driving point admittance for the given network. So first let us transform this into Laplace domain. 1 farad becomes 1 by S, 2 and 1 ohm resistor will remain same, and 1 Henry will become S. So these three are in series, so it becomes 3 by S, 3 plus S, this is 3 and S. So here, since these two are in series, 3 plus S will be in parallel with 1 by S. So Z of S will be nothing but 1 by S in parallel with 3 plus S. So if I simplify, I'll get S plus 3 by S square plus 3S plus 1. So if I want driving point admittance, is nothing but reciprocal of this expression, which is nothing but S square plus 3S plus 1 by S plus 3. So the eighth example just asks us to find the transfer function V2 of S by V1 of S, and also we have to find the expression for V2 of t, that is in time domain, if V1 of t is equal to 10 e power minus 2t volts. So first let us find this ratio. So on converting this in Laplace domain, so this will be 1 by 0.5s. So since there is no load connected, as I told you earlier, since assuming V1 to be an energy source connected between these two terminals, here there is no load connected, so we assume that the current flowing in this is 0, since there is no load connected to the second port. So on applying KVL or mesh to the first port, we will get 10 plus 1 by 0.1 S into I of S will be equal to V1 of S. So V2 will be nothing but voltage across this capacitor, which is 1 by 0.5 S into I1 of S. So the ratio of these two will give me, on simplification, 2 by S into 10 plus 2 by S. So here I have taken LCM of this expression. So now he has also asked us to find the expression for V2 of t. So given that V1 of t is equal to 10 e power minus 2t. So therefore from this V1 of S will be 10 by S plus 2. So V2 of S from this expression will be V1 of S into this expression, where V1 of S is nothing but 10 by S plus 2. So on simplification, I got the expression for V2 of S. So applying partial fractions, so on applying partial fractions, we will get the constant values K1 and K2. So on replacing the original expression and applying inverse Laplace to this, so V2 of t is equal to, this is in the form of 1 by S plus 2, so it is e power minus 2t. So here if I take 10 common from denominator, I will get S plus 0.2. So it will become e power minus 0.2t. So this is the expression for V2 of t for this network. Ninth example. So here he has asked us to find the value, the expressions, the expression for G21 of S, Z21 of S as well as Z11 of S. So since no load is connected here, I2 value becomes 0. So first let us find Z11 of S. So since this is open, these two becomes in series. So 10 ohm will be in series with 1 by 2s, which will be in parallel with 20 ohms. So on simplification, we will get the value of Z11 of S, which is nothing but V1 of S by I1 of S. So next let us see how to find the values of Z21 of S. So let us try to apply KVL to all the three loops. So here later we'll substitute I2 value to be 0. So the first expression will be 20 I1 minus I3 is equal to V1. The second mesh will be 10 I3 plus 1 by 2s into I3 plus I2, since both current directions are same, plus 20 into I3 minus I1, since here both are opposite in direction, is equal to 0. In the third mesh will be 1 by 2s into I2 plus I3 is equal to V2 of s. So from the second equation, if I simplify, 30 plus 1 by 2s into I3 of s minus 20 I1 of s is equal to 0. So this will give me relation between I3 of s and I1 of s. So in third equation, I'll substitute I2 to be 0. So which will give me V2 of s is equal to 1 by 2s into I3 of s. So this is your fifth equation. So Z21 of s is equal to V2 of s by I1 of s. We know the expression for V2 of s from fifth equation. And I1 of s I can write from fourth equation to be I3 into 60s plus 1 by 40s. So using these two expressions, I can write V2 of s by I1 of s to be this expression. So in other words, I have substituted the fourth equation in fifth equation, which will give me the value of Z21 of s. On simplification, we get 20 by 60s plus 1. Next, so in order to get the value of G21 of s, we have to take the ratio of V2 of s by V1 of s. V2 of s, as we know from equation 5, is I3 into 1 by 2s. So V1 of s, which is from first equation, 20 I1 of s minus 20 I3 of s. So here I can, on simplification, if I take both the ratios, which will give me the value of G21 of s, which is 1 by 20s plus 1. So here, in order to simplify this expression, we know that I1 of s, we have a relation in terms of I3 of s, equation 4. So using this relation, this expression, on simplification, we get this 60s plus 1 minus 40s by 2s. So therefore, in this way, this is the expressions for Z21 of s, G21 of s, as well as Z11 of s. Next, 10th example, whereas we have to find the expressions for Z11 as well as Z21 of s. So here, since no load is connected here also I2 value becomes 0. So on converting this into Laplace transform, the 2 ohms and 1 ohms will remain same. 1 farad becomes 1 by s and 2 farads becomes 1 by 2s. So let us apply KVL to both, to the first loop and the third loop, because the second loop, as we know, the current is 0. So let us consider first loop. So it is nothing but 2 into I1 minus I3 plus 1 by 2s into I1 is equal to V1. So similarly, the third loop will be, so this on simplification, if I take I1 common, it is 2 plus 1 by 2s minus 2 I3 is nothing but V1 of s, which we have considered as first equation. From second loop, there is a 1 by s into I3 plus 1 into I3 plus 2 into I3 minus I2 is equal to 0. So if I take I3 common, it is 1 by s plus 3, which will give me 2 into I1 of s. So let us consider that as second equation. So now I will substitute this in the first equation. So when I substitute this in first equation, it will give me I1 into, so here instead of I3 I have substituted 2s by 1 plus 3s into I1 of s. So on simplification will give me V1 of s by I1 of s, because we want Z11. So here in the first equation I want V1 by I1. So in order to eliminate I3, I have substituted the second equation in first equation. So on simplification will give me the value of Z11, which is V1 by I1 of S on simplification. But in this circuit, V2, as you know, is nothing but voltage across 1 ohm resistor as well as voltage across this capacitor. So that is, if I want V2 of S, it is nothing but 1 into the current flowing through 1 ohm resistor, which is I3, plus 1 by 2S into the current flowing through capacitor, which is I1 of S. So V2 is nothing but voltage across resistor as well as the voltage across capacitor. So from second equation, so using this relation, if we substitute here, which will give me the value of Z21, which is V2 by I1 of S. So on simplification, we get 4S square plus 3S plus 1 by 2S into 1 plus 3S. So this is how we find the Z21 of S as well as Z11 of S for this network. So the last sum in this concept. So they asked us to find the value of inductor L, and he has given the condition that Z of S is equal to 1. So first let us transform this network and try to find the expression for Z of S, and that expression will equate it to 1. So capacitor becomes 1 by S and inductor I will assume to be Ls. So since these two are in parallel and these two are in parallel and these two are in series, so this is 2 into 1s by 2 plus 1s, this is 5 into Ls by 5 plus Ls. These two parallel combinations are in series, so we have added. So on simplification, we will get the expression for Z of S. So this expression I have to equate it to 1 and find the value of Ls. So this expression I have equated to 1. So on cross multiplying, you will get this expression. On this, we will get the value of L. So this ends my tutorial lecture on network functions. So in next class, we shall see what are poles and zeros and what are their significance. Thank you.